Hello, this is Cary Hughes with MathWorks. In this video, I'm going to talk about modeling time delays in MATLAB and Simulink. Now, because this topic can grow quite large, this is going to be more of a part one video where I focus more on the MATLAB use case. All right, so why even bother modeling delay in the first place? Well, the short answer to that is delay is really a part of every system that you'll probably want to model. And so to model it with reasonable fidelity, you'll want to include delay and time as a part of that. Delay is also frequently a source of grief in modeling efforts, usually an underestimated source of grief at that. Delay takes on many forms that adds to the complexity of modeling it. It could be a discrete time signal, and that's a discrete time delay. It could be a continuous time delay. It could be a fixed delay. It could be a variable delay. And we have to account for all these different modeling scenarios. And even for a given modeling scenario, let's just take a simple fixed discrete delay. That itself could be modeled many different ways. So you're going to have to make decisions upon what is the best way to go about this. Different approaches are going to have different complexities, different runtime performances, maybe different readabilities. So lots of options to look at. And then, of course, delay, not only does it need to be modeled, but sometimes you need to change it or control it, and sometimes you need to measure it. We're going to focus more here on the modeling and or controlling it in this video. Delay is, again, everywhere. Again, model, control it, measure it. All analog digital filters have delay by definition. All transmission lines and communication channels, which are really forms of filters, have delay. Buffers and queues, FIFOs, flip-flops, those are all examples of really pure delay elements. Sometimes delay is desired, sometimes it's undesired, sometimes it's fixed, sometimes it's dynamic. Sometimes it's a matter of delay matching. So you got two signals, they're offset in time, so you need to add a delay to one signal to align it with another, and maybe that delay is going to have to be varied because the delay of the two signals between the two signals is also variable. All physical systems really have delay, even if it's very small, and all real world feedback systems by definition have delay, else that feedback system is not going to work in the first place. So again, delay is an easy concept to grasp. It seems very simple, but then it often becomes a source of grief in real world systems, both in the design and the modeling of those systems. Okay, now in this video or videos, we're going to focus only on the empirical use case of time or delay modeling. We're not really going into the symbolic analysis or frequency domain analysis of delay's effect on a system. So for instance, if you want to put a 200 millisecond delay in a system, that would be modeled as like an e to the minus 0.2s. So that would be the t is the delay value here of 0.2. So 0.2 milliseconds would be the delay. And of course, as we know, this has no impact on the magnitude response of the system from U to Y, but it does have an impact on the phase. It shifts the phase response downward. You basically lose phase with time delay. Again, we can model time and or delay in both MATLAB and Simulink, but the user experience is going to be quite different. We'll cover both environments eventually, but again, we're going to focus here on the MATLAB use case. And there are four use cases we typically want to cover in order to model delay or time in a more comprehensive manner. Now, MATLAB doesn't really have a built-in or native concept of time. And of course, you can't model delay without modeling time. They just go together. With a little work, however, you can kind of infer time in MATLAB, and that's what we're going to do here. And these are the four use cases. We got the first two, A and B, are discrete time use cases, a fixed discrete delay, a variable discrete delay. The third and fourth, C and D, are continuous time use cases. So we have a fixed continuous delay and a variable continuous delay. So let's start with the simplest case. That would be a fixed discrete delay. Y of n, let's say, is U of n minus 3. And we're going to take advantage of the ability to index into MATLAB arrays to do that. So we got two implementations here I'm showing for doing that. One is a batch-wise delay implementation. The other is a sample-wise delay implementation. For the batch-wise, it's pretty simple. We want to implement y of n equal u of n minus 3. So what we're going to do after we create our time vector and our signals, pre-allocate memory, etc., we're going to just assign a range of the input to a range of the output where the offset is built into the assignment. So delay plus 1, the 1 is there added to count for one base indexing in MATLAB. So that's pretty straightforward. For the sample-wise delay implementation, we have a for loop, and that looks more like the actual equation of what we want to implement. Y of n is equal to u of n minus 3. Here I just say y of k is equal to u of k minus delay, and that's all done inside of a for loop. Pretty straightforward. Now, the snag, of course, with the batch-wise implementation, although it's only a one-liner, is that doesn't work for variable delays. This is assuming here a fixed delay of some amount. All right, what about modeling fixed integer delays instead of just using indexing, using functions? In this case, I'm showing the linear buffering or linear indexing approach. So we got a function, it's called delay underscore 3, where the delay is fixed at 3 inside. And I'm doing my pre-allocation of a persistent array. And then there's basically two operations that go on here. We've got assignment of the output within the array, and then we've got our shifting of the delay line. This is almost easier to understand by looking at a picture. I've got my delay line of 3 elements. I've basically made an array out of that in MATLAB, x of 1, x of 2, x of 3, x of 4. I'm always going to write my input u of n to the first element, like you would assume in a system like this. You're shifting in elements, input elements into the first element. Here are the left-hand side of the pipeline. And then I'm going to take my output from the right-hand side. So if you think about this symbolically, it would be like, x of n minus 1, x of n minus 2, x of n minus 3. So x of n minus 3 here would be x of 1, which is y of n the output. So we always take the output from the last element. We always write the input of the first element. And this is great. It's intuitively simple. It's kind of like implemented like this picture, but it's very inefficient. So you can imagine if this pipeline were very long, like 1,000 or 1,000,000 elements, that we would be doing all of this data shifting without any really return on that effort. It'd just be a lot of cycles consumed, and we're just shifting elements along manually. So, while conceptually simple, it's extremely inefficient. Here's another way to do the same thing using functions, using a circular buffer, which is going to be significantly more efficient as the buffer gets long. So in this case, what we're going to do is we have a pointer, this circular pointer, you could say. And what we're going to do is only the pointer changes, but we don't have any shifting of the data. The only thing we do is, let's say the pointer is 2, we're going to write it to, well, element 2 in the array, wherever we assign element 2. And then the oldest sample in the array is 1 to the right of the current sample. That would be 3 in this case. And then you go in that case, and the next the oldest, and the previous, whatever. So always writing to the pointer location, and the pointer moves. Okay. So at the next time step, pointer is equal to 3. We write to this element. The oldest is always 1 to the right. That would be u of n minus 3. So we take the output from there. So this is fairly simple. It's not insurmountable, but it is tedious. It's not very intuitive. It's just a glance at the code and figure out what it's doing. But it is, again, more efficient than the linear indexing approach. Now, no discussion of this topic would be complete without mentioning that DSP System Toolbox does provide time delay objects. Now, really, it's really not quite accurate to call them time delay, because really they're sample delay objects. They're really no concept of time here, but you can say you can implement y of n equal u of n minus 3 pretty easily. You just create an object, a system object, dsp.delay of 3. I'm calling that D3. And now I can apply D3 to my input signal to form my output signal. So notice all the indexing and buffering is kind of taken care of for you. You can implement this also in a sample by sample use case, as I'm showing here, or you can use a vector-based case where, again, there's no indexing at all. It just does it all for you. You can also implement, there's also objects for variable integer delays, dsp.variable integer delay, where you can implement u of n minus d of n, where d of n is changing at each time step, or it could be a variable fractional delay, where here again, f of n doesn't have to be an integer, it could be 1.3692, it could be any fractional number you put in there, any positive fractional number. So these are very convenient system objects if you need to implement variable delays or variable fractional delays. Keep these in mind. So how about modeling continuous time signals and variable time delays in MATLAB, like y of t equal u of t minus t, or tau of t. So tau of t, of course, is changing as a function of time, or delay value. So you can do this in MATLAB, and here I'm showing one very straightforward way to do that. You create your time vector, create your input signal, say I'm going to delay it by 1.5 seconds, and then you can use a function like linear interpolation to interpolate between basically one time vector and another, from the t time vector to this t minus delay time vector. And that's one way to do it. Now, this is a batch processing approach. This is not really showing you how to do this in a typical simulation where you're streaming time samples in one sample at a time. This doesn't really tell you anything about how you would construct such a system. It just says interpolate from this time vector to another time vector. Okay, well, we can do it. And this doesn't really work if delay is changing as a function of time. Notice here, it's fixed at 1.5 seconds. This does not support the d of t or tau of t use case. So we have to do something else to account for that. So how would we model a continuously varying time delay? So in this case, I'm showing that y of t is equal to u of t minus d. And again, where d is changing as a function of time, basically everything here is changing as a function of time. So the way we would do that is I'm going to call this the look back technique. So we say we're at somewhere in the middle of our simulation, we're humming along, we're at time ti, that's some instantaneous point in time, and we want to know what that output is based on our delay. Our delay is di, it could be changing, but at that particular time instant, the time delay is di. We look back into our input buffer. We assume we're collecting some input buffer as we're doing this delay operation, and it could be whatever samples. We want to make sure that buffer is reasonably large to account for the maximum delay we need to model. We look back di seconds, and we notice that in our buffer there's no sample at di seconds, but we do have a sample before and after it. So we're going to grab those before and after samples. We're going to do a linear interpolation or some type of interpolation between those before and after samples, and we're going to write that result of that interpolation right here in our output buffer. And then we're going to step time, the current simulation time, to the next step, and step and repeat the exact same process. So that works. And the way you would write that code looks something like this, or at least one possible way to do this. I've got my setup code here on the right where I create a particular signal, test signal, and then I've got the actual implementation on the right where I step the time vector along and do the interpolation, and I do the finding of the A and the B points. That's the line right above it where I find the time sample right after the time delay and right before it, do the linear interpolation and step and repeat. Again, this does require a sufficiently large input buffer to account for all the delay scenarios you need to account for. It does support variable time step, although I'm showing a fixed time step use case. It's backward looking, as I said, and it does require some caution. And I'm not going to get into all those kind of edge use cases here, but there can be use cases where you get a result which is maybe not expected or undesired, maybe doesn't match the modeling scenario you had in mind. But for most use cases, this is going to work. And here's one example where I have a delay, which is a ramp signal that increases in a stepwise linear fashion. So the delay starts out very small, a fraction of a second, and then steps in like 80 millisecond increments each second up to about 80 something milliseconds of delay, or 800, I should say, milliseconds of delay. And the input signal is also a ramp, a stepwise ramp signal in red. And then the delay version of it is in blue. And you can see the incremental delay as we increase the delay here. You can see the blue signal is just incrementally delayed with respect to the input red. All right, that's really all I wanted to say. I'm going to transition really in the next video to go into how we can do a lot of the same operators of continuous discrete time delays in Simulink, and hope you'll stay tuned with me for that. Thank you.